Hello, my name is Ashley Nyhan, and today I conducted an executive summary of a 20-page paper entitled Tissue-Specific Engineering, 3D Bioprinting in Regenerative Medicine. For this presentation, I'm going to be introducing you to the topic at hand, 3D bioprinting, taking you through the paper by section, and finally reviewing the paper. The introduction of this paper answers the question, what is 3D printing? A main problem in the medical community today is finding a way to successfully reconstruct and replicate tissue in a way that allows disease-ridden tissues to regenerate via the fabrication of fine and detailed structures, all while preventing their decomposition and maintaining functional integrity. 3D bioprinting does just this, allowing for the construction of cells and tissues while simultaneously preventing decomposition and treating patients with congenital diseases, degenerative diseases, and trauma. The success of 3D bioprinting relies heavily on engineers to create machinery that has the ability to replicate cells and tissues in ways that are not only affordable but also readily available and efficient. This brings us to the first section of the paper entitled Functional Tissue Engineering, which ultimately answers the question, what types of tissue are being replicated? Depending on the type of tissue that is being reformed, there are specific materials and techniques that need to be utilized to successfully replicate their unique functions and structures. Most forms of 3D printed biotissues are created in the form of scaffolds, replacing diseased organs and tissues. Epithelial cells typically line the outside of an individual's body and act as a protectant to them from outside particles. This means that the 3D printed scaffold should have little to no space in between cells, in turn forming a sort of sheet or tubular structure. These cells have a high sensitivity to many chemical and physical substances, so it is very important for the printing process to take place in a safe and enclosed environment. Connective tissues is one of the most common types of tissue engineering due to their ability to differentiate into other types of tissue like bone, tendon, and meniscus. Through the years, synthetic biomaterials have been created that mimic the stiffness and viability of these cells, allowing these scaffolds to be replicated for the human body. The high complexity of nerve tissue has made them the most difficult to create a tissue engineering strategy for. The structures and scaffolds of these tissues are very elaborate due to the complexity of the central nervous system, peripheral nervous system, therefore forcing the success of the replication to rely mostly on the architectural construct and many times hindering their results. When reforming muscle tissue, it is very important that they have the ability to contract just like normal muscles do. Muscle tissues also have a very complex microstructure that must be considered when refabricating these muscles, which makes the fabrication very difficult. The next section is entitled Bioprinting Technologies for Tissue Engineering and answers the question, what are the different types of bioprinting? Bioprinting is a process that allows the fabrication of tissue structures and scaffolds by allowing a direct spatial arrangement of various cells and materials using a material called bioink. The first method of bioprinting is called inkjet bioprinting, which uses a method of placing droplets that contain cells onto a substrate, therefore creating patterns layer by layer. Also referred to as lift. Laser-assisted bioprinting uses laser beam pulses to print cells by the generation of small, high-pressure bubbles of hydrogel, which adhere to a substrate. Extrusion is the most popular and widely used bioprinting process due to its lower cost, good cell viability, decent speeds, and its ability to use a wider range of bioinks. But the cell deterioration for this method makes it difficult to print large tissue constructs. In situ bioprinting is a method in which cells are printed directly into an individual's body. This method is mainly used to print an entire organ into the body during an operation and has been used in the past to repair skin, heart valve defects, and bone defects in mice. 4D bioprinting is a new design for bioprinting that incorporates the variable of time, allowing for the change of shape and function of tissues over differing periods of time. There are many different studies and tests that are currently being conducted to discover more about 4D printing and the benefits of its future use. The next section is called Biofunctional Materials for Tissue-Specific 3D Bioprinting and answers the question, what materials are being used? For 3D bioprinting to be successful, there is a need for materials that do not induce any toxic responses within patients and that are synthetic or natural integrals. Some materials include natural and synthetic polymers. Natural and synthetic polymers are some of the most highly used biocompatible materials to rebuild tissues. Both types of polymers have their benefits, with natural polymers providing a better microenvironment and synthetic polymers having more flexibility when it comes to property control. Decellularized matrix components are of major benefit since they are taken directly from the target tissue directly, which in turn helps in the preservation of the structure and scaffold of those cells. On the other hand, this method sometimes requires very large tissue samples, which at times is impossible to do. Ceramics are often used to replicate bone structures due to chemical and physical similarities. At times, ceramics and polymers are combined due to the fact that the combination of these two materials resembles bone structure most accurately when used together. The next section is Bioprinting Applications of Tissue-Specific Tissues in Histology, answers the question, how does this apply? This section goes into detail about many of the tests that have been conducted concerning each type of tissue, including data, facts, and figures to go along with the descriptions provided. The main types of different reconstructions are also described in detail. For example, the epithelial tissue reconstruction mostly involves skin, the cornea, blood vessels, and the human liver. Each type of tissue reconstruction has its downfalls, some including low resolution, high cost, and time-consuming conflicts. Yet, there is a lot of future potential and benefit that can come from additional research and discovery. The final section is Conclusions and Future Prospects, which answers the question, what now? There are still many problems within the topic of tissue reconstruction, meaning that there is a lot of future research that needs to be conducted. First and foremost, it is vital that tissue-specific engineering starts with the potential issues of the disease-ridden tissue of focus. Furthermore, some future research includes the understanding the possible need for different regeneration techniques depending on the age of the individual at hand, as well as needing compatibility of sterilization tools with different materials within the 3D regeneration process. This brings me to my overall review of the effectiveness of this research paper. Overall, this research paper was highly effective in many ways, yet might need some work in a couple of areas. Although the ideas within this research paper were separated very nicely, leaving readers with a good idea of where one topic ended and another began, it can be surmised easily that this paper is meant for health professionals to read, as most terms were left undefined, making it necessary for unknowledgeable readers to conduct more outside research. In the future, it is suggested that writers add more detailed descriptions of some of the more general ideas, so that interested yet unqualified readers would have better understanding of the topics mentioned within the paper. The Bioprinting Applications section of the paper seemed to have so much information packed into one section, it became confusing to read and understand, making it difficult for readers to obtain much helpful information about the histories of various reconstructions. I believe that the 4D printing section of the paper would be a better fit towards the conclusion, since there has not been a lot of research conducted about the topic, and it could be described as a point for future research instead. The conclusion of the paper seemed to be well organized and thought out, and there were a wide range of future research and application options, giving other experienced individuals the opportunity to join the conversation and conduct more research. This is my works cited. Thank you so much and have a